Right now, you are sitting inside the one object in the universe you will never see from the outside, the Milky Way, too vast and too close to step back from. No eye, no spacecraft, no telescope has ever looked back and caught its true shape. And yet we know it has a barred center, great spiral arms, and a vast invisible halo holding everything together. By the end of this video, you will understand how astronomers drew the map of a place no one has ever seen from outside, tracing its arms in the dark from within, and why the shape they found is the reason you are here to ask about it. Go outside on a clear night, far from the lights of any town, and you can see the thing itself. A pale band of light runs across the sky, faint and slightly ragged, brighter along some stretches and thinner along others, as though someone had dragged a brush of mist from one horizon to the other. It does not look like much. It looks like weather, or like a faint smear left on the dark. For almost the whole of human history, that soft ribbon was simply part of the night, as ordinary and as unexplained as the wind. That ribbon is the galaxy, seen from the only angle we are ever allowed. Our sun sits buried inside a flattened sheet of stars, and when you look toward the band, you are looking edgewise through that sheet, the long way, through hundreds of billions of stars too far off and too tightly crowded for your eye to pull apart. Their light runs together into a single haze. When you turn and look away from the band, you are looking out through the thin face of the sheet into emptier space, where the stars thin and the dark takes over. The band is not a thing painted across the sky. It is the disk of our own galaxy, viewed from a seat deep inside it, and that seat is the worst place imaginable from which to learn the shape of something. We are not standing outside the Milky Way, pointing inward, the way we point a telescope at a distant spiral and watch its arms wind clearly against black space. We are within it, moving with it, made from its material, carried around its center along with everything else we can see. To draw an honest map of a galaxy, you would want to rise high above its disk and look down on the whole pattern at once. We cannot rise at all. We are a single fixed point, set roughly 2/3 of the way out from the middle, turning slowly in the plane of the very thing we are trying to picture. Imagine being handed a blank sheet and asked to draw an accurate street map of a vast city you have never once seen from above, at night, on foot, in a low fog, with no map of your own. You can make out the few buildings nearest you and a brighter glow rising from somewhere busier across town. You can sense a darker district where the lamps have failed, but distances deceive you. A lit window close at hand and a floodlit tower far away look equally near. Streets bend out of sight behind walls. You can never climb high enough to take in the plan as a whole. Everything you come to know, you learn from inside, one street and one glimpse at a time, and you must assemble the city in your mind from fragments that never quite line up. That is precisely the problem the Milky Way sets. Clouds of dust hide whole districts of it from view. Near stars and far stars overlap along the same line of sight, so that a faint nearby ember and a brilliant distant beacon can sit side by side in the sky and give no hint of which is which. And the center of the galaxy, the one landmark that would orient everything else, the hub the whole structure turns around, lies behind such thick curtains of gas and dust that for most of history no one could see it at all. The single most important feature of the map was the one feature the eye could never reach. From a seat like that, it should not be possible to know the shape of the galaxy at all. If you find these reflective explorations of the cosmos meaningful, a like or a subscribe helps us continue making them. And yet somehow, we do have the map. Not a vague impression, but a real detailed measured shape. Some of it is even hidden in plain sight in that band overhead, if you know how to read it. Look again on a dark night, and the river of light is uneven, swelling into a broad, bright knot in one direction, thinning almost to nothing in the other. That lopsidedness is not decoration. It is the long view inward, toward the crowded heart of the galaxy, set against the short view outward toward its sparse edge. The naked eye is already reading the structure, without understanding a word of it. And from that faint, unresolved smear, by patient steps, astronomers have drawn out something extraordinarily specific. We can say that the Milky Way is a flattened disk, roughly 100,000 light-years across, with a bright bar of older stars laid across its middle, several spiral arms trailing out from the ends of that bar, and our own sun set quietly between two of them, about 26,000 light-years from the center. We can say that the disk is not perfectly flat, but lifts and dips at its outer rim, warped gently like the brim of a hat. We can say that around all of it lies a halo of something that gives off no light whatsoever, yet outweighs every glowing star and cloud combined. We can say how fast the whole thing turns, roughly when it last tore apart and swallowed a smaller galaxy, and where, tonight, new stars are being pressed into being. We can describe a structure that no member of our species has ever laid eyes on, and we can be confident we have it close to right. How is that possible? That is the real question, and it is stranger than the shape itself. Not one line on that map was simply seen. Every arm, every distance, every hidden mass was inferred, drawn out of starlight and radio noise, and the slow drift of motion by people who never once left the disk, who solved the puzzle of a structure from a seat locked permanently inside it. The galaxy did not show them its shape. They reasoned it into view. The answer took more than 200 years to assemble, and it did not arrive cleanly. The first confident maps were badly wrong in ways that would take generations to undo, and the people who drew them were not careless. They were doing everything right with the tools they had, and still arriving at a false picture. The breakthroughs, when they came not from looking harder but from changing the question. From learning to measure distance where the eye gave no clue. From discovering the very substance that had been hiding the view. And finally, from giving up on sight altogether and learning to listen to the galaxy in forms of light no human eye can register. Each step solved one problem and immediately exposed the next. The shape of the Milky Way was not discovered in a single moment of revelation. It was earned, slowly, against a perspective built to withhold it. But long before any of that, before the rulers and the radio dishes, before anyone thought to ask how far away the band of light might be, the Milky Way was not a structure at all. It was a story, told and retold across every culture that ever looked up. And the map of our galaxy, oddly enough, does not begin with an instrument. It begins with the moment a few people stopped asking what that river of light overhead might mean, and started asking, instead, what it actually was. For thousands of years, no one asked what the band of light was made of, because the question did not seem to be that kind of question. The pale river overhead was not a problem to be solved. It was a presence to be named, and almost every people who lived under dark skies gave it a name and a story. To the Greeks, it was a trail of milk, spilled across the heavens, a goddess turning her face from a child at her breast, the spray of it frozen into the sky. That single image has outlasted every myth around it. The word galaxy comes straight from the Greek for milk, and the older name, the Milky Way, is simply a translation of the Latin via lactea, the road of milk. We still call the largest structure we belong to by a word that means a stain of milk on the dark. Elsewhere, the band became a river more often than a road. Many cultures saw a great celestial water, a silver stream flowing through the night, sometimes the heavenly twin of a river on the ground, the Nile or the Ganges raised into the sky. Some saw a path, a road walked by the dead, or by the gods, or by birds migrating south. Others saw a seam, a backbone, a rope of smoke from a great fire. The specifics differed, but the instinct was shared. The band was read as something laid across the sky from outside, a feature of the heavens with a meaning attached, placed there for us to interpret. A few traditions did something stranger, and, in hindsight, sharper. Instead of reading the bright band, they read the dark patches inside it, where dense clouds blot out the glow, leaving holes and lanes of blackness. Some people saw shapes in the darkness itself. Across the southern sky, several Aboriginal Australian traditions trace an emu, not from stars but from the dark dust lanes that run along the band, a great bird picked out in shadow rather than light. In the high Andes, the Inca read animals into those same dark rifts, dark shapes, within a celestial river. They did not know it, but they were looking directly at the very thing that would later hide the galaxy from its first mapmakers, the clouds of dust strung through the disk. They had simply chosen to see the obstruction as a picture rather than a problem. There is something fitting in that. The first people to take the dark patches seriously were not astronomers with instruments, but observers with patience. And the lanes they turned into birds and foxes were the very same lanes that would, centuries later, defeat the finest telescopes ever pointed at the galaxy's heart. For all their variety, every one of these readings answered the same kind of question. They asked what the band meant, who had placed it there, and what it signified for the people beneath it. None of them asked what it physically was, what it would turn out to be if you could reach it and take it apart. And the one ancient answer to that physical question that came closest to the truth was, for nearly 2,000 years, the one almost no one believed. The dominant view inherited from the Greek world came from Aristotle, and Aristotle placed the Milky Way below the stars entirely. To him, it was not a thing in the heavens at all, but a kind of weather in the upper air, a glowing exhalation, a haze kindled high in the atmosphere beneath the sphere of the moon. On this account, the band was local, terrestrial, closer than the planets, a fog belonging to Earth rather than to the cosmos. That idea held for centuries, partly because it came stamped with Aristotle's authority, and partly because, from the ground, there was simply no way to test it. Against it stood a much older and bolder guess. Long before Aristotle, the atomist Democritus had proposed that the soft glow was not vapor and not a single substance, but the merged light of a vast multitude of stars, each one too faint and too closely packed for the eye to separate. It was a remarkable intuition, arrived at by reasoning alone, and it happened to be right. But a guess that cannot be checked is not yet knowledge, and for 2,000 years there was no instrument on Earth that could decide between a glowing fog and a crowd of distant suns. The matter rested, unresolved, a story with no way to end. Then, in the winter of 1609 and into 1610, a man in Padua pointed a new kind of instrument at the sky. Galileo had built himself a telescope, crude by any later standard, a tube with two small lenses that gathered a little more light than the naked eye, and magnified what it gathered. He turned it on the moon and found mountains. He turned it on Jupiter and found moons. And he turned it on the pale band of the Milky Way, and there the soft, continuous glow simply dissolved. Where his eye had seen a smear, the telescope showed stars, not a handful, but a swarm, more than he could count, packed so densely and so faintly that their light had blurred together into the haze everyone had always seen. He wrote it down plainly in his little book of discoveries, The Starry Messenger, published in 1610. The galaxy is nothing other than a mass of innumerable stars gathered together. It was a short sentence with an enormous consequence. On the very best night, far from any light, the unaided eye can make out a few thousand stars in the whole sky. Galileo's crude tube revealed that behind nearly every patch of apparent emptiness lay countless more, and that the soft river overhead was simply the direction in which the suns were stacked most thickly. The cosmos had, in a single winter, grown vastly larger than anyone had been counting on, and the Milky Way had become the most crowded road through a universe suddenly brimming with stars no eye would ever resolve. The question of meaning was, in that moment, quietly replaced by a question of measurement. Democritus had been right, and Aristotle wrong, and the band overhead was settled at last as a real thing made of real objects, countless suns, scattered through space, seen edge on from somewhere, within their crowd. That single observation changed the category of the thing entirely. A road of milk or a celestial river is something you contemplate. A collection of stars is something you can interrogate. You can ask how many there are. You can ask how far away they reach. You can ask whether they thin out at the edges, where their center lies, and what shape they make when taken all together. For the first time, the Milky Way had become a structure, and a structure can, in principle, be mapped. But Galileo's telescope, for all that it had answered, opened a far deeper difficulty in the same instant. It had proved the band was stars. It had not, and could not, say where any of those stars sat in depth. Through the eyepiece, a star was still only a point of light, brighter or fainter, but giving no honest clue whether it was a modest sun close by or a brilliant one impossibly far away. The swarm had no front and no back that the eye could read. Galileo had turned a glowing fog into a field of countless points, and in doing so had revealed that the real problem was not what the Milky Way was made of, but how those pieces were arranged across distances no one yet had any means to measure. The shape of the galaxy was now, for the first time, a fair question. Answering it would require a way to tell near stars from far ones, and the first person to attempt the map in earnest would not wait for such a method. He would simply assume one, count what he could see, and from that bold assumption build the most careful, most detailed, and most thoroughly mistaken picture of the Milky Way that anyone had yet produced. The man who tried it was William Herschel, and he was, by some distance, the finest telescope builder of his age. German-born, settled in England, he ground his own mirrors and built instruments larger and sharper than anything the professional observatories possessed, working through the night with his sister Caroline beside him, recording every figure he called down to her from the eyepiece. Caroline Herschel was an astronomer in her own right, a discoverer of comets, and the two of them together swept the sky more thoroughly than anyone before them. It was Herschel who, in 1781, had discovered a new planet, Uranus, the first world added to the solar system in all of recorded history, and the fame that discovery brought him paid for ever larger mirrors, culminating in a monstrous instrument 40 feet long that he aimed up into the dark like a cannon. So when Herschel set out, in 1785, to determine the actual shape of the star system the Sun belonged to, he did so with the best eyes on Earth and a method of disarming simplicity. He counted. In direction after direction across the sky, he pointed his telescope and counted the stars he could see in the field of view, sampling hundreds of separate patches of the heavens. He called these counts his star gauges. The reasoning behind them rested on a single bold assumption, that the stars were spread more or less evenly through space, and that all of them shone with roughly the same true brightness, so that a faint star was simply a distant one, and a bright star, a near one. If that were true, then the number of stars he could see in a given direction told him how deep the system ran that way. Where he counted many stars, the galaxy stretched far. Where he counted few, it came to an end close by. By gauging the star counts all around the sky, he believed he was sounding the depth of the Milky Way in every direction, the way a sailor sounds the floor of a harbor. When he assembled the results into a diagram, a shape emerged. It was an irregular, ragged slab, far longer than it was thick, flattened and split at one end, with the stars crowding toward a central plane and thinning above and below it. It looked something like a grindstone or a cloven disc, and there, set almost exactly in the middle of it, sat the Sun. It was the first map of the Milky Way ever built from real measurement rather than myth, and its central conclusion was that we lived close to the heart of the whole structure. For a first attempt, made with the right instinct that the band was a flattened system of stars seen from within, it was a genuine achievement. It was also wrong, and Herschel, to his great credit, came to suspect as much himself. The trouble lay buried in his one assumption. Stars are not all of equal brightness, not remotely. A truly luminous star and a feeble one can differ in real output by factors of thousands, so that a brilliant sun far away and a dim sun nearby can present the eye with exactly the same faint point of light. Brightness, the very thing Herschel had leaned his entire method on, is not a reliable measure of distance at all. Over his lifetime, he grew uneasy. He noticed regions his largest telescope could not seem to fathom, places where the stars simply ran out before any edge should have appeared, and he began to wonder whether his instrument was truly reaching the bounds of the system or merely failing part way. The grindstone, magnificent as it was a portrait of how far Herschel could see, not of how far the galaxy extended. More than a century later, the method was rebuilt with far greater rigor, and it arrived at the same answer. The astronomer this time was Jacobus Kapteyn, a Dutchman at the University of Groningen, who possessed no great telescope of his own, and so did something new. He gathered photographic plates and catalogs from observatories around the world and subjected them to relentless statistical analysis, measuring not just how many stars lay in each direction but how bright they appeared, how fast they drifted across the sky, and what those motions implied about their distances. It was patient, industrial work, carried on for decades, and it represented the most careful accounting of the stellar system that anyone had ever undertaken. He even organized astronomers across the world into a single coordinated campaign, dividing the whole sky into a couple of hundred chosen fields that observatories everywhere agreed to photograph and measure in exactly the same way, so that for the first time the galaxy was being surveyed by a planet working in concert. The result, published around 1922, the year Kapteyn died, became known as the Kapteyn universe. It was a flattened lens of stars, perhaps 40,000 light-years across, and several thousand thick, dense at the middle, and fading smoothly toward its edges. And once again, near the center of that lens, only slightly off from the very middle, sat the Sun. Two of the most thorough surveys in the history of astronomy, separated by more than 100 years and built on entirely different data, had independently placed humanity almost exactly at the heart of the galaxy. When two careful, independent methods agree, it is usually a sign that they are right. This time, it was a sign that they shared the same hidden flaw. That flaw was the dust. Strung through the disk of the Milky Way, in the same dark lanes the old observers had turned into emus and rivers, lies a thin haze of fine grains that absorbs and scatters starlight. It is not thick, a spacecraft would pass through it unaware, but it is vast, and across the enormous distances of the galaxy its effect accumulates relentlessly. Light from a faraway star is dimmed and reddened and, beyond a certain depth, snuffed out entirely. It also leaves a fingerprint as it goes, tinting the surviving light faintly red, a clue that sat in the data for decades before anyone learned to read it. Crucially, this dust sits all around us within the plane of the disk, so it dims the view in every direction along the band by roughly the same amount. And that is what springs the trap. Imagine standing in a forest on a foggy day. In every direction, the trees fade into gray and vanish at about the same distance, so the clearing of visibility around you looks circular, with you at its center, even if you are standing at the very edge of the wood. The fog does not just hide the far trees, it convinces you that you are in the middle of everything. The dust does exactly this to an observer inside the disk. It cuts off the view at a similar range all around, so the galaxy appears to thin out symmetrically and end not far away, with us conveniently in the middle. It shrinks the apparent system, and it centers us within it, both at once. Kapteyn, to his credit, suspected something like this might be happening. He searched his data for signs of a dimming material spread through space, understanding that if it existed, his whole model would collapse. He looked, and concluded the effect was too small to matter. It was the single most consequential wrong turn in the story, made by one of its most careful minds, and it left the false map standing. There was an irony in all of this that no one yet felt the weight of. 3 centuries earlier, Copernicus had pushed the Earth out of the center of the cosmos and set it turning around the sun, and the long shock of that demotion had reshaped how people understood their place in things. Yet here, at the largest scale anyone could measure, humanity had quietly crept back to the middle of everything, seated near the heart of the entire star system, as though the universe were arranged around us after all. It was a comfortable position, and it was about to be taken away for good, so the trap closed. The eye had been beaten, and now the most rigorous counting had been beaten too, defeated by something it could not see, and had been talked out of believing in. To break free, astronomers needed something the whole method had lacked from the beginning, a way to measure the true distance to a remote object directly, without assuming anything about how bright it ought to be, and ideally using objects bright enough to be seen straight through the haze. That tool was about to arrive. It would not come from a grand telescope or a famous observatory, but from a particular kind of pulsing star, and from a woman sitting at a desk in Massachusetts, comparing photographic plates of the sky by eye. Her name was Henrietta Swan Leavitt, and she did not work at a telescope. She worked at a desk on the upper floor of the Harvard College Observatory, in a room full of women bent over glass photographic plates, measuring the positions and brightnesses of stars by eye and recording them in neat columns, day after day. The observatory's director had hired a whole staff of them, paying them around 30 cents an hour to do the painstaking arithmetic of astronomy, work considered too tedious for the men, who used the telescopes at night and handed down the plates to be processed by the women in the daylight. They were called computers, because computing was their job, long before the word meant a machine. Among them were several brilliant astronomers whose names the science would eventually be forced to remember. One, Williamina Fleming, had been the director's housekeeper before he set her to classifying stars, and she turned out to have a gift for it. Another, Annie Jump Cannon, would go on to sort hundreds of thousands of stars into the sequence of stellar types still in use today, working with a speed and accuracy no one has matched since. They sat together in a converted room, each paid a fraction of a man's wage, and between them they quietly laid down much of the foundation of modern stellar astronomy. Leavitt was assigned the variable stars, stars whose brightness does not hold steady but rises and falls, dimming and recovering on a regular beat. She was, by then, growing deaf, the result of an illness, and there is something quietly apt in the image of a woman losing one sense while training another to an extraordinary degree of precision. Plate after plate, she compared photographs of the same patch of sky taken on different nights, hunting for the points of light that had changed in brightness between one exposure and the next. It was relentless, repetitive work, and she was exceptionally good at it. Over the years, she identified thousands of variable stars, more than anyone else alive, a great many of them in 2 faint smudges of light visible only from the southern hemisphere, the Magellanic Clouds, photographed for Harvard from a station high in the mountains of Peru. Those 2 clouds, it would later turn out, are themselves small galaxies in their own right, companions bound to the Milky Way and slowly falling toward it. But to Leavitt, they were simply rich fields of stars, conveniently gathered together at a single great distance, and that convenience was about to matter enormously. It was in the smaller of those two clouds that she noticed something the rest of the world had missed. Among her variables was a particular kind of star, one that pulses with a smooth, clockwork regularity, the type now called a Cepheid. As she catalogued the Cepheids in the small Magellanic Cloud, sorting them by how long each took to complete one full cycle of brightening and dimming, a patterned surface that was almost too clean to be real. The stars that pulsed slowly, taking many days to run through a cycle, were consistently the brightest. The ones that pulsed quickly, in a day or two, were consistently the faintest. The longer the beat, the brighter the star. The relationship was so tight that she could plot it as very nearly a straight line. She first reported the hint of it in 1908, and by 1912, she had pinned it down firmly with 25 of these stars, the pattern clean and unmistakable. What made this possible was the very thing that had defeated Herschel and Kapton. Inside our own galaxy, brightness tells you nothing certain, because a faint star might be dim and near or brilliant and far, and there is no way to know which. But all the stars in the small Magellanic Cloud sit together at very nearly the same enormous distance from us, the way the windows of a distant town are all about equally far away from someone watching from a hill. Their differences in apparent brightness, therefore, were not differences in distance. They were real differences in true output. For the first time, the confusing variable of distance had been held fixed, and the underlying law could be seen plainly. A Cepheid's pulsation period is tied directly to its actual luminosity. That single fact turned a pulsing star into a ruler for the universe. The logic is beautifully simple. Find a Cepheid anywhere in the sky, watch it for a few nights, and time its beat. From the period alone, Leavitt's relation tells you how much light the star is truly pouring out, its real brightness, regardless of where it sits. Then compare that to how bright it merely appears from Earth. A star that should be brilliant, but looks faint, must be far away, and exactly how faint it looks tells you exactly how far, because light fades with distance in a precise and known way. A Cepheid, in other words, announces its own true brightness by the rhythm of its pulse, and any star that tells you its true brightness can tell you its distance. After centuries of guessing, astronomers finally had an honest yardstick they could lay across space, one that did not depend on assuming all stars were alike, and Cepheids were the ideal stars to carry it. They are giants, some of them tens of thousands of times more luminous than the sun, pulsing on periods that run from about a day to over a month, bright enough to be picked out one by one, not only across our own galaxy but deep into others, beacons still legible at distances where ordinary stars dissolve into an unresolved haze. A faint star makes a poor signpost. A brilliant one keeping perfect time can be read from very far away indeed. There is a reason these particular stars keep such reliable time. A Cepheid is a star passing through a brief, unstable phase of its life, in which a deep layer within it acts like a valve, trapping heat, swelling outward, then releasing and falling back, over and over. The star physically breathes, and the size of the star sets the tempo. A larger, more luminous Cepheid is like a bigger bell, ringing with a slower, deeper note, taking longer to complete each swing, while a smaller one rings quick and faint. The brightness and the rhythm are bound together by the star's own structure, which is why the period can betray the luminosity at all. Leavitt had found the law without needing to know its cause. The clockwork was real, whether or not anyone understood the gears. She was not permitted to follow where it led. The director kept her on the cataloging, the measuring, and recording, and steered the work of turning her relation into actual distances to others. The calibration that would anchor her law to a real scale, pinning down the true distance to even one nearby Cepheid, so that all the rest could be read absolutely, was carried out by other hands. Her name slipped off most of the discoveries built on her measurement. She died of cancer in 1921, at 53, and 4 years later a mathematician wrote to nominate her for the Nobel Prize, unaware that the prize is never given to the dead and that she had already been gone for years. The single most useful tool in the history of cosmic distance was assembled by a woman, paid by the hour to do what others considered drudgery, who never got to point it at the sky herself. The rung she had cut into the ladder would, within 2 decades, let others reach so far beyond the Milky Way that they proved the spiral nebulae were entire galaxies in their own right, and caught the whole universe in the act of expanding. But all of that was still to come. The first thing her ruler would measure was closer to home, but the tool existed now, and it was about to be used to do something Leavitt's relation made possible for the first time. to measure not the distance to a star, but the distance to a whole crowd of them, and from those distances to locate the true center of the Milky Way. Someone was about to take her ruler, point it not into the crowded plane of the disk, where the dust still blinded everyone, but up and out of it, at a strange scattering of dense star cities that hung above and below the galaxy, and use what he found there to throw the sun out of the center of the map at last. The man who picked up Leavitt's ruler was Harlow Shapley, working at the Mount Wilson Observatory in California, where the largest telescope in the world at the time was pointed at the sky. Shapley had become fascinated by a class of object that did not behave like ordinary stars, the globular clusters. A globular cluster is a tight, roughly spherical swarm of hundreds of thousands of old stars, bound together by their own gravity into a dense ball that can be seen, through a good telescope, as a grainy knot of light. These clusters are among the oldest structures in the entire galaxy, balls of stars that formed in its earliest days and have survived almost unchanged ever since, ancient relics wheeling on long, looping orbits that carry them far out of the disk and slowly back. Roughly 100 of them were known, and they had one peculiar habit that turned out to be the key to everything. They did not lie in the flat band of the Milky Way with the other stars. They hung above and below it, scattered through the empty space around the disk, many of them riding high out of the plane entirely. That single fact freed Shapley from the trap that had caught everyone before him. The dust that dimmed and shortened every view along the disk was concentrated in the plane itself, in that same thin band. The globular clusters, floating above and below it, could be seen across clear lines of sight that the haze barely touched. For the first time, an astronomer had a set of bright, distant landmarks he could survey without the fog lying about their distances. And Shapley had exactly the means to measure how far away they were, because the clusters were full of pulsing stars, RR Lyrae variables, close cousins of Leavitt's Cepheids, each one announcing its true brightness by the rhythm of its beat. By timing those pulses and comparing true brightness to apparent brightness, he could lay Leavitt's yardstick across the gulf to each cluster in turn. It was the first time anyone had measured honest distances to objects so far beyond the immediate neighborhood of the sun, and the numbers that came back were enormous, tens of thousands of light years, reaching out into a space far larger than the modest lens Kapteyn had been prepared to draw. Then he did something simple and inspired. He reasoned that the globular clusters, swarming through the space around the galaxy, ought to be arranged symmetrically about its true center, the way a cloud of bees orbits the hive rather than any one flower. If that were so, then the center of their distribution would mark the center of the Milky Way itself, wherever that turned out to be. So he measured the distance and direction to cluster after cluster, and plotted where they sat in space. The result was not symmetrical around the sun at all. The clusters were lopsided, overwhelmingly piled up toward one quarter of the sky, toward the constellation Sagittarius, and the center of their great swarm lay far off in that direction, tens of thousands of light years away. There was a quiet vindication in that direction. Look back at the band of the Milky Way on a dark night, and its brightest, densest stretch, that broad, luminous knot low in the summer sky, lies in Sagittarius. The naked eye had been pointing at the center of the galaxy the whole time, drawn to the glow of its crowded heart without anyone realizing that was what they were seeing. The single most important clue had been hanging overhead in plain view for the whole of human history. It simply took Leavitt's ruler, laid across a swarm of ancient clusters, to finally read it. The conclusion was unavoidable, and it was staggering. The sun was not at the center of the galaxy. It was not even close. The true heart of the Milky Way lay in the direction of Sagittarius, and our solar system sat far out toward the rim of the disk, an ordinary location in the suburbs of a structure whose middle was somewhere else entirely. Shapley had taken the comfortable map that Herschel and Kapteyn had built, the one with humanity seated near the center of creation, and he had pushed us out to the edge of it. Around 1918, looking at the smudged knots of light hanging above the galaxy, he had completed the demotion that Copernicus had begun. First, the Earth had been moved from the center of the solar system. Now the sun itself was moved from the center of the galaxy. We were not the hub of anything. We were riders far out on a turning wheel, looking in toward a center we could not even see clearly for the dust. It was a humbling result, delivered without drama by a man patiently counting the beats of faint stars in distant clusters, and the universe had used it to inform us, once again, and more emphatically than before, that it had not been arranged around us. It was, in the broad strokes, correct, and it remains one of the great reorientations in the history of science. But Shapley got the scale badly wrong in the other direction. His Milky Way came out enormous, far larger than it truly is, with the center much further away than it really lies. The actual distance from the Sun to the galactic center is about 26,000 light-years. Shapley's figure was roughly twice that. He had been bitten, in his own way, by the same dust that had fooled Kapteyn. It dimmed even some of his cluster stars, making them seem more distant than they were, and inflating his whole galaxy. So the two great errors of the age were mirror images. Kapteyn had the size closer to right, but put us at the center. Shapley moved us correctly off the center, but blew the size up far too large. Each had been deceived by the unseen haze, in opposite directions, and neither yet had a way to measure exactly how much that haze was stealing. The disagreement came to a head in the spring of 1920, in a now famous confrontation staged before the National Academy of Sciences in Washington. It is remembered now simply as the Great Debate, and what hung on it was nothing less than the size of the universe. Whether the Milky Way was the whole of creation, or one island among countless others, and whether it spanned tens of thousands of light-years or hundreds of thousands. Almost nothing about the scale of existence was yet agreed upon. On one side stood Shapley, with his vast galaxy and the Sun cast out toward its edge. On the other stood Heber Curtis, who held that the Milky Way was much smaller, closer to Kapteyn's modest lens. The two men were also arguing about something even larger, the faint spiral nebulae scattered across the sky. Curtis insisted these were island universes, whole separate galaxies, far beyond our own, each one a Milky Way in its own right. Shapley insisted they were minor objects lying within or near our galaxy, because to him our galaxy was so immense that it might as well be the entire universe. The strange thing about that debate is that each man was half right and half wrong. Shapley was correct that the Sun sits far from the center, but wrong that the spirals lay inside our galaxy. Curtis was correct that the spirals were distant galaxies, but wrong that the Sun sits near our center. The true shape of things lay scattered between the two of them, and neither could assemble it alone. The question of the spiral nebulae would be settled within a few years, when Edwin Hubble found Cepheids, Leavitt stars again, inside the great nebula in Andromeda, timed their pulses, and proved it lay far outside the Milky Way, a separate galaxy beyond anything Shapley had imagined. Curtis had been right about that, but the question of our own galaxy's shape and true size remained tangled, because the one thing standing between every astronomer and a trustworthy map was still uncharted. The dust had distorted Herschel, fooled Kapteyn, and inflated Shapley. Until someone could prove that this invisible material was really there, strung through the disk, and measure precisely how much light it stole over a given distance, no map of the Milky Way could be trusted. And that proof was about to come from an unlikely quarter, not from staring at the galaxy's grand structure, but from the patient study of ordinary star clusters, and the discovery that they were not quite as far away as they looked. The man who finally caught the dust in the act was Robert Trumpler, a Swiss astronomer working at the Lick Observatory in California, and he did it almost by accident, by paying close attention to a humble kind of object. The open star clusters scattered through the disk. These are looser, younger gatherings than Shapley's great globular swarms, a few hundred to a few thousand stars, drifting together through the plane of the Milky Way. Trumpler set out simply to catalog them and understand them better, and to do that he needed to know how far away each one was. He had two entirely separate ways of working that out, and the quiet disagreement between those two methods would crack the whole problem open. The first method used brightness. By examining the kinds of stars a cluster contained, Trumpler could estimate how much light they truly gave off, then compare that to how bright they appeared, and from the shortfall calculate the distance, the same essential logic Leavitt had made possible. The second method used size. If open clusters are, on average, roughly the same true physical size, then a nearer cluster should look larger in the sky, and a more distant one should look smaller, in simple proportion to its distance. So the apparent width of a cluster gave him a second, independent estimate of how far away it lay, owing nothing to brightness at all. It was a little like judging how far away a person stood in two different ways at once by how small they looked, and once by how faint their voice sounded, and trusting the two estimates only where they agreed. For nearby clusters, the two methods agreed nicely. But as Trumpler looked at clusters further and further out along the disk, the two answers began to part company, and they parted in a very particular, very telling way. The distant clusters were too faint. Judged by their apparent size, they sat at a certain distance. but judged by their brightness, they appeared dimmer than they had any right to be at that distance, as though something had stolen a portion of their light on the way to us. And the discrepancy was not random. The further away a cluster lay, the fainter it appeared relative to its size, the loss mounting steadily with distance. There was only one explanation that fit. The space between the stars was not empty. Something filled the plane of the disk, thinly but pervasively, absorbing starlight as it crossed. And the more space a beam of light had to traverse, the more of it was swallowed before it arrived. It was the signature of a toll gate placed not at any single point, but along the entire length of the road, charging a little more for every additional stretch of space the light was forced to cross. In 1930, Trumpler published the result, and it was as close to direct proof as astronomy could ask for. Interstellar matter was real, it pervaded the disk, and it dimmed everything seen through it in steady proportion to the distance traveled. He could even put a number to the theft, a measurable loss of light for every 1,000 light-years a beam crossed within the plane, so that astronomers now possessed not merely the fact of the dust, but a rate, a correction they could apply to peel apparent distances back toward true ones. He could even measure its other fingerprint. The dimming was not even-handed across all colors of light. The distant clusters were not merely fainter than they should be, they were also redder. Their light shifted subtly toward the warmer end of the spectrum. This is exactly what fine grains of material do. Particles comparable in size to the wavelength of light scatter blue light far more readily than red, so that a beam passing through a long column of such grains arrives both weakened and reddened, its blue stripped away preferentially, its red surviving better. Sunsets on Earth glow red for the very same reason, as light grazes a long, dusty path through the atmosphere. The reddening Trumpler measured proved that the absorbing material was not some abstract fog, but real, solid grains, interstellar dust, strung through the spaces between the stars. We now know roughly what that dust is. It is made of grains far smaller than anything you could see, smaller than the particles in smoke, flecks of carbon, and silicate minerals, soot and sand at the scale of a few 100,000ths of a millimeter, forged in the cooling outer layers of dying stars and flung into space to drift among the gas. By mass, it is a trifling component of the galaxy, barely 1% of the thin material between the stars, which is itself a whisper compared to the stars themselves. And yet this faint smoke is extraordinarily good at blocking visible light, precisely because its grains are tuned to the wavelengths our eyes use. A trace of it, spread across thousands of light years, is enough to draw a curtain across the galaxy. There is a real strangeness in this, worth pausing on. The very material that hides the galaxy from us is also the material the galaxy builds with. Those same grains of carbon and silicate are the seeds of new worlds. In cold, quiet clouds they clump together, gather into pebbles and boulders, and over long ages assemble into rocky planets like the one beneath your feet. The dust that blinds the astronomer is the same dust that became mountains and ocean beds, and, through a long chain of chemistry, the very atoms now reading these words. What stands in the way of seeing the galaxy is, quite literally, what we are made from. The obstacle and the origin are one substance. And that curtain hangs, crucially, in the plane of the disk, in the very band where the stars are thickest and the center lies. With the dust finally proven and measured, the broken maps suddenly made sense. Every earlier error fell into place at once. Kaptein's lens had looked small and sun-centered because the dust cut off the view at a similar distance all around, springing the trap exactly as a fog springs it in a forest. Shapley's galaxy had ballooned too large because the same dust had dimmed his cluster stars, making them seem further away than they were. Correct for the absorption, and both distortions shrink toward the truth. The great debate could at last be scored with some honesty. The galaxy was indeed large, though not the monster Shapley had drawn, and the sun did indeed sit far out from its center, exactly as he had argued. The galaxy was not Kaptein's modest lens, nor Shapley's bloated giant. The sun sat far from the center, as Shapley had said, about 26,000 light-years out, within a disk roughly 100,000 light-years across. For the first time, the numbers on the map were close to right, and the reason they had been wrong for so long was no longer a mystery. It had been the dust all along. But the same discovery that fixed the map also delivered a hard verdict. The dust was not merely a correction to be applied, it was a wall. In the plane of the disk, the absorption is so severe that toward the galactic center, that bright knot in Sagittarius, the single most important place to see, Only a vanishing fraction of the visible light ever struggles through. The heart of the Milky Way is buried behind so many curtains of dust that to ordinary starlight it is, for practical purposes, utterly opaque. The dimming toward the core runs to something like a factor of a trillion. For every trillion photons of visible light that set out from the center, only a single one survives the journey to our eyes. No sharper lens, no larger mirror, no darker mountaintop would ever change that. Visible light simply could not reach us from the regions that mattered most. To map the center and the crowded far side of the disk beyond it, astronomers would have to abandon the only kind of light their eyes and telescopes had ever used. They would have to find a messenger that the dust could not stop. And the grains that block starlight so completely happen to be almost perfectly transparent to a different kind of light entirely. A faint radio whisper that a young Dutch student, working in a country under occupation, was about to predict before anyone had ever heard it. The way past the wall was to stop using light the eye could see. Visible light is only a narrow slice of a vast spectrum of radiation, a single octave in a range that runs from gamma rays shorter than an atom to radio waves longer than a building. What separates these forms of light is simply their wavelength, the distance from one crest of the wave to the next, and that single property turns out to decide everything about whether dust can stop them. The grains of interstellar dust are tiny, a fraction of the wavelength of visible light, and that is precisely why they block it so well. They are sized to catch exactly those waves. But radio waves are enormous by comparison. Their crests separated by centimeters or meters, rather than fractions of a thousandth of a millimeter. To a radio wave, a dust grain is not an obstacle at all. The wave simply rolls past it, the way a long ocean swell rolls past a floating cork without noticing it is there, while the same cork would block a ripple in a pond. Radio light pours straight through the curtains of dust that stop starlight dead. There was already a hint that the radio sky held something worth hearing. Back in 1932, an engineer named Carl Jansky, hunting for the source of static interfering with transatlantic radio calls, had found a faint hiss coming from the sky itself, and the hiss grew loudest when his antenna pointed toward Sagittarius. He had, without quite realizing it, picked up radio waves streaming from the center of the galaxy. The very region the dust had kept permanently hidden from every telescope on Earth was, in the radio band, the brightest thing in the sky. The direction we could not see at all was the direction shouting loudest. Jansky published his discovery and was then, to the lasting regret of astronomy, moved on to other work, and it would be more than a decade before anyone built on it in earnest. But the radio window onto the galaxy was open. The problem was that a vague hiss is not a map. To map the galaxy, astronomers needed more than noise. They needed a clean, sharp signal at a single known wavelength, a spectral line produced by some specific substance spread throughout the galaxy that could be traced from place to place, and whose pitch could be measured precisely. And there was an obvious candidate, if only it would speak. Hydrogen, the simplest and most abundant element in the universe, fills the space between the stars in enormous cold clouds of single atoms, neutral and dark. It is the raw material of the galaxy, more plentiful than everything else combined, threaded through the entire disk. This is the reservoir from which all future stars will be drawn. Every star the Milky Way has yet to make is waiting, for now, as cold hydrogen adrift in the dark. The trouble was that cold neutral hydrogen, drifting quietly in the dark, gives off no visible light. The most common substance in the Milky Way was also one of the most invisible. If there were only some faint signal it emitted, something in the radio band that could slip through the dust, it would light up the whole structure of the galaxy from within. It turned out there was, buried in the deepest physics of the atom. A hydrogen atom is the simplest thing in chemistry, a single proton with a single electron. Both the proton and the electron behave as though they are spinning, each carrying a tiny magnetic property, and those two tiny magnets can sit in one of two arrangements, aligned with one another or opposed. The aligned arrangement holds a sliver more energy than the opposed one. Every so often, with no warning and no cause, an atom in the higher arrangement flips to the lower one, and in that instant, it sheds its scrap of surplus energy as a single particle of radio light, with a wavelength of precisely 21 centimeters. For any one atom, this flip is almost unimaginably rare. Left to itself, a given hydrogen atom waits, on average, around 11 million years before it happens. It is the faintest, slowest signal imaginable. But the galaxy holds such a staggering number of hydrogen atoms, beyond all counting, that at every moment a vast multitude are flipping somewhere, and the combined effect is a steady, gentle hum at 21 centimeters, rising from every cloud of hydrogen in the Milky Way, a whisper from each atom, once in an age, a continuous chord from the galaxy as a whole. It is worth dwelling on the trick of scale that makes this work. No single atom could ever be caught flipping. The event is too rare and too faint by an incomprehensible margin. But raise the number of atoms high enough, fill 1,000 light-years of space with them, and then 100,000 more, and the impossibly improbable becomes the perfectly steady. The galaxy turns rarity into reliability simply by being enormous. The man who worked all of this out had never heard the signal, and could not have, because no instrument yet existed to detect it. He was Hendrik van de Hulst, a young Dutch astronomer, and he made his prediction in 1944, in the Netherlands, in the depths of the German occupation. These were the darkest years the country had known. The universities had been throttled, Leiden's among the first to be closed after its staff protested the dismissal of their Jewish colleagues. The senior astronomer Jan Oort, who had grasped before almost anyone what radio astronomy might do for the study of the galaxy, had withdrawn from Leiden in protest and was waiting out the war in the countryside. And yet, even then, the science continued in quiet corners. Oort posed the question of what kinds of radio signals the galaxy might emit, and Van de Hulst, working through the physics, arrived at the answer. Neutral hydrogen should ring, faintly but detectably, at a wavelength of 21 centimeters. He presented it at a small gathering of astronomers in occupied Leiden, a prediction with no means whatever of being tested, made by a young man in a starving, blacked-out country, about a note the galaxy had been singing, unheard, since long before there were ears to hear it. That same winter would come to be known in the Netherlands as the Hunger Winter, a season of famine in which thousands died of cold and starvation while the occupation ground on. To sit down in such a time and reason out the exact wavelength at which the hydrogen of distant space must ring is a particular kind of act, a quiet refusal to let the mind be shrunk to the size of the emergency. The galaxy did not care about the war, and for a few hours at a desk, working through the arithmetic of a spinning electron, neither did the question. It took 7 years for the world to recover enough to listen. In the spring of 1951, a pair of physicists at Harvard, Harold Ewan and Edward Purcell, built a horn-shaped antenna, pointed it at the Milky Way, and caught the 21-centimeter line for the first time, exactly where Van de Hulst had said it would be. Within weeks, the Dutch themselves confirmed it, along with a group in Australia. The Dutch had in fact been racing to detect it first, and might well have succeeded, but a fire had destroyed their receiver the year before and cost them precious time. In the end, the three teams published together, the prediction and the detection now joined across an ocean and half a decade. The faint chord of hydrogen, predicted from pure reasoning in the dark years of the war, was real, and it was pouring through the dust unimpeded, carrying news from every corner of the galaxy that visible light had never been able to reach. But hearing the note was only the beginning. A steady hum tells you hydrogen is there. It does not, by itself, draw a map. The thing that would turn that single tone into the first true picture of the Milky Way's hidden shape was a subtlety hidden in the note's pitch, the way the wavelength shifts, ever so slightly, when the gas emitting it is moving toward us or away. And the people who would seize on that shift and use it to trace the spiral arms of the galaxy, one slow measurement at a time, were the very same Dutch astronomers who had predicted the signal in the first place. The subtlety hidden in the note was the Doppler effect, the same thing you hear when an ambulance passes on the street. As the siren races toward you, its pitch rises, the sound waves bunched up by its approach. As it recedes, the pitch drops, the waves stretched out behind it. Light behaves in exactly the same way. A cloud of hydrogen moving toward us compresses the 21-centimeter waves it emits, shortening them a fraction. A cloud moving away stretches them, lengthening them a fraction. By measuring precisely how far a cloud's signal has drifted from its true 21 centimeters, an astronomer can read off how fast that cloud is moving toward us or away, to remarkable accuracy. The shifts involved are minute. A cloud sliding along at the speed of a fast aircraft moves the line by less than 1,000th of its wavelength, but radio receivers can measure them with ease, far more finely than any shift in visible light could be read. The motions of the galaxy, wholly invisible to the eye, were written cleanly into the radio signal for anyone with an instrument to read them. Suddenly, every patch of hydrogen in the galaxy was reporting two things at once: that it was there and how it was moving along our line of sight. That second number was the one that broke the problem open because of the way the galaxy turns. The Milky Way does not rotate like a solid wheel, with everything swinging round together. It rotates differentially. The gas and stars near the center complete their orbits faster than those further out, in the same general way that the inner planets race around the sun more quickly than the outer ones. This was not a new idea. Decades earlier, in the 1920s, building on work by the Swedish astronomer Bertil Lindblad, Jan Oort had proved, from the drift of nearby stars, that the galaxy must rotate in just this fashion, with inner regions outpacing outer ones. So, when the hydrogen line arrived, Oort already knew how the galaxy spun, and that knowledge was the missing key to depth. Here is why. When a radio telescope looks out along a single line of sight through the disk, it gathers the 21-centimeter signal from many separate clouds at many different distances, all piled up along the same direction. To the eye, as we have seen, such clouds would be hopelessly confused, near and far indistinguishable. But each of those clouds, sitting at a different distance from the center, is moving at a slightly different orbital speed, and so each shows a slightly different Doppler shift. The signal coming back is not a single tone but a spread of them, a chord, each note corresponding to gas at a particular velocity, and therefore, through the known pattern of galactic rotation, at a particular distance along the beam. By untangling that chord, astronomers could finally place hydrogen clouds not just in direction, but in depth, sorting the near from the far by the pitch of their song. It is worth letting the strangeness of that sink in. There was no way to see how far away a given cloud of gas lay, no ruler that could reach it, no parallax, no standard candle buried inside it to time. And yet, simply because the whole galaxy turns in an orderly way, the speed of a cloud quietly betrayed its distance. Motion had become a substitute for sight. The astronomers were not photographing the galaxy at all. They were deducing its three-dimensional shape from the music of its own rotation. The dimension that had been missing since Galileo first resolved the band into points of light, distance along the line of sight, was at last recoverable, not by seeing it, but by listening to how the galaxy moved. The people who set out to do this in earnest were Oort and his colleagues at Leiden, and they began, fittingly, with an instrument of war. Their first radio dish was a captured German radar antenna, a Würzburg reflector left behind from the occupation, repurposed at a site called Kootwijk to listen for the hydrogen line their own Van de Hulst had predicted. An instrument built to hunt aircraft was turned to the patient mapping of the galaxy. There was a quiet symbolism in it that the astronomers themselves felt. The same wartime technology built to track bombers across the sky now tilted upward, in peacetime, to trace the slow drift of hydrogen across a galaxy that had been turning indifferently through the whole of the war and everything before it. With it, and then with far greater reach, the Dutch began the long labor of sweeping the northern sky, direction by direction, recording the velocity spread of hydrogen across the Milky Way. In 1956, they completed a far more powerful instrument at Dwingaloo, a single steerable dish 25 meters across. For a brief while, the largest radio telescope in the world, built on the quiet heathland of the northern Netherlands, specifically to carry this work forward. Oort was the steady force behind all of it, not the man at the eyepiece so much as the one who had seen what the hydrogen line could become, who organized the surveys, secured the instruments, and held the long project together across years. Under his direction, Leiden became, for a generation, the center of gravity of the entire field. The work itself was unglamorous beyond description. Point the dish, record a trace, shift the pointing by a fraction, record again, thousands upon thousands of times over, assembling a map of the invisible one, narrow strip at a time. Year by year, the map filled in. Sweeping the sky and untangling the velocity cords was slow, meticulous work. But as the measurements accumulated, the hydrogen of the Milky Way arranged itself, on the charts, into long, curving features, not a uniform haze, but extended lanes of gas sweeping out from the inner galaxy in great arcs. The Dutch surveyed the sky they could reach from the northern hemisphere. Astronomers in Australia surveyed the southern sky the Dutch could not see. In 1958, the two halves were stitched together into a single picture, and there, for the first time in human history, was a map of the spiral arms of the Milky Way, traced in neutral hydrogen drawn by people who had never left its disk. The galaxy was a spiral. It had arms, and from the steady march of the Doppler shifts across the sky, it was unmistakably turning, a great slow wheel of gas and stars, carrying everything, including us, around a center we still could not see. It was the vindication of a prediction made at a desk in an occupied country a little over a decade earlier. Van de Hulst's faint, theoretical note had become the surveyor's chief instrument, and with it, the Dutch had done what Herschel, Kapteyn, and Shapley, for all their labor, could never quite manage. They had drawn the true plan of the galaxy, arms and all, from a seat locked inside it. The map was a triumph, and it was also, honestly, imperfect. Converting velocities into distances meant trusting the assumed pattern of rotation, and where that pattern was uncertain, the distances blurred. Along some lines of sight, the method was genuinely ambiguous, a single velocity matching two possible distances, so that gas near and far could be confused. The arms came out soft-edged and approximate, their exact courses open to argument. But for all that, the essential thing was now beyond doubt. The Milky Way was a rotating spiral galaxy, and its broad architecture could be charted from within, by listening rather than looking. Yet the very rotation that had drawn the arms also raised a deep and immediate problem about them. If the inner galaxy truly swings round faster than the outer galaxy, then any pattern stamped into the disk should wind itself up like cream stirred into coffee, the inner part racing ahead, the whole structure smearing into a tight blur within a few turns of the wheel. Picture a spiral drawn on the surface of a whirlpool. Within moments, the inner part overtakes the outer. The curve winds tighter and tighter, and the pattern tears itself into a smear. The galaxy has turned dozens of times since it formed. By rights, the spiral arms should long ago have wound away to nothing, and yet there they were, clear and open and persistent. Whatever the spiral arms were, they could not be solid lanes of fixed gas and stars caught in the rotation. They had to be something stranger, and working out what would change the meaning of the word arm entirely. The puzzle was sharp and unavoidable. The spiral arms were plainly there, traced in hydrogen across the whole disk, open and graceful. Yet the galaxy's differential rotation should have destroyed any such pattern long ago. If an arm were a fixed ribbon of particular stars and particular clouds, strung out across the disk, then the inner end of that ribbon, orbiting faster, would race ahead of the outer end, and the arm would coil tighter and tighter with every passing rotation until it wound away into a featureless smear. After dozens of rotations, the Milky Way should be smooth. It is not. The arms persist, generous and well-defined, across a span of time long enough to have erased them many times over. The only way out of the contradiction was to stop thinking of an arm as a thing, and start thinking of it as an event. The resolution, when it came, was as elegant as the puzzle was stubborn. A spiral arm is not a structure made of fixed material. It is a pattern, a traveling region of slightly higher density that moves through the disk as a wave, while the actual stars and gas flow in through one side of it and out through the other. The arm is not the matter, the arm is the crowding, and crowding can persist in a place, or move at its own slow pace, even as the individual things doing the crowding are constantly being replaced. The clearest way to feel this is to think about a traffic jam on a motorway. Imagine a slow lorry laboring along in the middle lane. Behind it, cars bunch up, forced to brake and crawl, packed close together in a dense knot of traffic. That knot is real. You can see it from a helicopter, a visible region of high car density on the road, and it can persist for hours, even drift slowly along the motorway. But it is not made of any particular cars. Cars arrive at the back of the jam, inch their way through the crush, reach the front, and accelerate away, off about their business. The cars are always changing. The jam stays. The dense patch is a pattern that individual vehicles pass through, not a convoy of fixed ones traveling together. If you photographed the jam at noon, and again an hour later, it would look much the same, yet not one of the same cars would be in it. The jam even keeps its own speed, quite separate from the speed of the cars. It can sit nearly still, creep slowly forward, or in heavy traffic drift backward against the flow, all while the cars themselves move briskly through it. The pattern and the matter are simply two different things, traveling at two different rates. A spiral arm is exactly this, written across a galaxy. The disk is full of stars and gas, all orbiting the center, and the spiral pattern is a slow-moving wave of enhanced gravity and density, turning through that disk at its own stately pace, generally slower than the stars themselves orbit. A star out in the disk, swinging round on its orbit, gradually catches up with an arm from behind. As it enters the denser region, the extra gravity of all the crowded matter there tugs at it, slowing it slightly and holding it a while, just as a car slows entering the jam. The star lingers in the crowd, then carries on round its orbit and exits out the leading edge of the arm, speeding back up and sailing on into the thinner spaces beyond. Our own sun has passed through spiral arms many times in its long life, and will again. There is even one special distance from the center, which astronomers call the corrotation radius, where stars happen to orbit at exactly the pattern's own pace, and so travel along with an arm, rather than streaming through it. Almost everywhere else in the disk, matter and pattern slide endlessly past one another. The arm is not a place where the same stars live permanently. It is a place where stars are always slowing down, piling up, and moving on, the wave standing while the matter streams through it. This single idea dissolved the winding problem completely. Because the arm is a wave and not a material ribbon, it does not get wound up by differential rotation. The matter wins. The pattern need not. The wave can hold its open spiral shape for a very long time, even as countless stars and clouds pour through it and out the other side. It also explained, beautifully, why the arms shine. As a great cloud of cold hydrogen, exactly the gas the radio surveys had been tracing, drifts into a spiral arm and is squeezed by the crowding, the compression can tip the densest parts over the edge into collapse. You can often see the squeeze itself in photographs of other spirals. A sharp, dark lane of dust runs along the inner edge of each bright arm, marking the very front where the wave first compresses the gas, just upstream of where the new stars flare into being. Gravity takes hold, and new stars ignite. The arms, in other words, are the galaxy's nurseries, the places where the cold reservoir of gas is pressed hard enough to give birth. And among the newborn stars are a few rare giants, enormously massive, burning blue-white and ferociously bright. These brilliant stars are also short-lived, racing through their fuel in just a few million years, far too quickly to drift any meaningful distance from the arm before they die. So they live and die close to where they were born, outlining the spiral arm in brilliant blue light, like lamps marking the crest of the wave. This is why, in photographs of other spiral galaxies, the arms blaze blue and bright against the smoother golden disk. The arms are not where most of the stars are. They are where the newest and most luminous stars are, lit up exactly where the density wave has most recently squeezed the gas into life. Our own sun was kindled in just this way, billions of years ago, in some long since dispersed arm, out of a cloud of gas and dust pressed together by a passing wave. In the most literal sense, we are a product of the spiral pattern that still turns overhead. The idea had deep roots. Back in the early decades of the 20th century, the Swedish astronomer Bertil Lindblad, the same Lindblad whose work on rotation had guided Oort, had argued that spiral structure must be bound up with the patterns of stellar orbits rather than with fixed lanes of matter. But the full theory, the one that made the mathematics work, came in 1964 from two astronomers in the United States, Chia Lin and Frank Hsu. They showed how a spiral density wave could maintain itself as a long-lived, slowly rotating pattern in a disk of orbiting stars, turning the loose intuition into a rigorous account of how a galaxy could wear open arms for billions of years without winding them shut. It was a subtle and beautiful piece of physics. The wave was not imposed on the disk from outside. The star's own gravity sustained the very pattern that organized them, the disk holding its own shape in place through a kind of collective feedback, the arm feeding the gravity that fed the arm. That self-sustaining quality was precisely what had eluded everyone who tried to picture spiral structure as fixed lanes of matter. It would be wrong to leave the impression that the matter is fully settled, because it is not. The clean picture of a single, steady, long-lived wave works better for some galaxies than others, and modern simulations suggest many spiral arms are more changeable than the early theory implied, forming, dissolving, and reforming over time rather than turning rigidly like a fixed pinwheel. The Milky Way's own arms are a case in point. Messy, uneven, some of them grand and sweeping, others mere spurs and fragments, their exact number and shape still argued over today. But the central reconception holds, and it is one of the loveliest in all of astronomy. A spiral arm is not an object you could point to and say it is made of these stars. It is a wave you can stand inside, a place the galaxy crowds together, that endures while everything in it flows through and moves on. And we do stand inside this turning, wave-cross structure, at one very specific address. Not in the blaze of an arm, as it happens, but just off to one side of it, in a quieter corner whose particular location, it turns out, may have a great deal to do with why anyone is here to map the galaxy at all. Our address, written out in full, begins with a distance. The sun lies about 26,000 light-years from the center of the galaxy. That is far. Light itself, the fastest thing there is, needs 26,000 years to cross the gap between us and the hub of the Milky Way. So the light arriving now from the galactic center set out when the last ice age still gripped the northern world, and no city had yet been built. We sit roughly 2/3 of the way from the center to the visible edge of the disk, neither in the crowded heart nor out on the lonely rim, but in the broad, quiet middle reaches, the suburbs, if you like, of a very large city. The visible disk of stars reaches out to perhaps 50,000 light-years from the center in every direction, so at 26,000 we sit a little past the halfway mark, set down in open country between the bright inner galaxy and its thinning outer edge, and we do not even sit in one of its grand avenues. The Milky Way's major spiral arms are great sweeping structures, the Sagittarius arm curving by on the inner side of us, the Perseus arm lying further out, and the sun belongs to neither. Instead, we occupy a smaller, more modest feature that runs between the two big arms, long known as the Orion Spur, or the local arm, a sort of side street branching off the main thoroughfares. For decades, it was regarded as a minor offshoot, a fragment of an arm rather than the real thing. More recent radio measurements, timing the precise positions of star-forming clouds, have suggested it is rather more substantial than that, a respectable structure in its own right. But it remains a quieter place than the blazing major arms, a spur off to one side of the brightest activity, and that, as it happens, may be no small detail in the story of our being here. This position is also why the band of the Milky Way looks to us the way it does. When we gaze toward Sagittarius, low in the summer sky, we are looking inward across 26,000 light-years toward the bright, crowded bulge, the densest, most luminous stretch of the whole band. When we turn and look the opposite way, toward the outer rim, the band thins and fades, because there are simply fewer stars stacked up behind one another in that direction, and the dark rift that splits the summer Milky Way down its length is the dust of our own Orion Spur, the nearby lane of the very material that hid the galaxy from its mapmakers for so long. The shape of our address is written into the sky overhead, for anyone who knows how to read it. Around this distant point, the sun is traveling, and it is not traveling slowly. We are sweeping along our orbit around the galactic center at something like 230 kilometers every second, fast enough to cross the distance from one side of a country to the other in a heartbeat, fast enough that the figure barely seems believable. And yet, set against the sheer scale of the galaxy, even that tremendous speed is stately. The circle we are tracing is so enormous that a single lap around the center takes roughly 230 million years. Astronomers call that span a galactic year, and it dwarfs every human measure of time. In the entire 4.5 billion years since the Sun and Earth formed, we have completed only about 20 laps. The Milky Way, ancient as it is, has turned barely 20 times beneath us. That single fact rearranges one's sense of history. The last time the Sun was at this same point in its orbit, the first dinosaurs were appearing on a younger Earth. The whole age of the dinosaurs, their rise and their reign and their sudden end, occupies most of one galactic year. Go back a handful of galactic years, and there were no animals on land at all. Go back 20, to the Sun's very first lap around the center, and the Earth was a young, barely cooled world, without a single fossil to its name. The galaxy has made only about 20 of these vast revolutions in the entire history of our solar system, and life has needed a good fraction of them simply to climb from single cells to creatures capable of looking up and counting the turns. All of recorded human history, every empire, and every life that has ever been written down, amounts to perhaps a few thousandths of a single lap, a tiny arc, barely a flicker of motion along an orbit that will go on turning for billions of years more. We are not so much traveling through the galaxy as being carried by it, slowly, on a journey whose single revolution outlasts entire ages of life on our planet. The orbit is not a flat, perfect circle either. As the Sun sweeps around the center, it also bobs gently up and down through the plane of the disk, like a horse on a carousel that rises and falls even as it goes round. Each time the Sun drifts a little above the midplane of the disk, the combined gravity of all the stars and gas below pulls it back down. It overshoots, sinks below the plane, and is drawn up again, oscillating slowly through the disk as it orbits. One full up and down bob takes something like 60 million years, carrying us a few hundred light years above the plane and back. Some researchers have wondered whether these slow risings and sinkings, by sweeping the sun through denser layers of the disk, might leave faint imprints in the long history of our planet. It is a speculative notion, far from established. What is beyond doubt is the motion itself. We are never quite still with respect to the plane, but always rising or settling through it on this long, slow rhythm. At this moment, as it happens, the sun sits slightly above the midplane and is still drifting upward. We are gently riding the swell of the disk even as we circle its center, all of it unfelt, all of it utterly silent beneath the steady appearance of the night sky. There may be more riding on this quiet location than mere coordinates. Our spot in the galaxy is, by the standards of the Milky Way, a remarkably peaceful one. We are far from the violent crowded center, with its crushing density of stars, its fierce radiation, and the great dark mass that lurks at the very middle. We sit between the major arms rather than within one, and the arms are where the action is, where gas is squeezed, where massive stars flare and die, where supernovae detonate most often. Drifting through the calmer lanes between them, our solar system may have been spared the worst of that turbulence for long stretches of its history. There is a real idea here, which astronomers sometimes call the galactic habitable zone, the notion that there is a comfortable band within a galaxy, not too close to the deadly center, not too far out, where the raw materials of planets grow scarce, where stable, life-friendly conditions are most likely to persist. The heavier elements that planets and bodies are built from were forged inside generations of earlier stars, and they lie richest toward the crowded center and grow scarcer toward the rim. Somewhere in between is a band with enough of that enrichment to build rocky worlds, yet enough distance from the center to stay calm. It is an idea still argued over, not a settled law, and it would be a mistake to claim our survival was guaranteed by our address. But the broad point stands. The long, uninterrupted calm that complex life seems to require was far more likely to be found in a quiet spur, far from the center, on a gentle and well-behaved orbit, than in the blazing heart of the wheel. Where we happen to sit and how steadily we happen to move are not unrelated to the fact that anyone has been here long enough to wonder about it. So this is our place, far out, off to one side, riding slowly up and down as we circle a center once every few 100 million years. For the whole of this story, we have been describing the calm outskirts, the structure as seen from a peaceful seat near the rim. But that center we have been quietly orbiting all this while, the bright knot in Sagittarius, the hub, the whole vast wheel turns around. The one place the dust had hidden most completely was now, at last, beginning to give up its secrets to the radio and infrared eyes that could pierce the veil. And what lay there turned out to be stranger and more extreme than anything out in our gentle suburb. Traveling inward from our quiet spur, across the calm middle reaches and through the bright major arms, the galaxy changes character entirely. The stars crowd closer and closer together until, in the innermost few thousand light years, they pile into a dense, swollen concentration that astronomers call the bulge. If our own neighborhood is open country, the bulge is the packed old quarter at the heart of the city, where the buildings stand shoulder to shoulder and the streets are ancient. The stars here are old, most of them, red, long-lived suns that formed in the galaxy's earliest days and have been circling the center ever since. Their ages reach back close to the birth of the galaxy itself, which makes the bulge a kind of living archive of the Milky Way's beginnings, its formation written in old starlight. To the eye, this whole region is invisible, buried behind the thickest dust of all. But infrared light, with wavelengths longer than the eye can see, slips through that dust far better than visible light does. And when astronomers built instruments to map the center in the infrared, the bulge emerged from behind its veil at last, a great glowing mass of crowded ancient stars. The crowding there is difficult to picture. Where the sun drifts through near emptiness, its closest neighbor light years away, a world near the galactic center would lie beneath a sky ablaze with stars, thousands of them bright enough to read by, packed so tightly that close encounters and near collisions, vanishingly rare out in our calm suburb, become ordinary events. It is an old, dense, restless place, and almost none of it can be seen in ordinary light at all. And when they looked closely at the shape of that mass, they found a surprise that rewrote the galaxy's classification. The center was not a simple round ball of stars. It was elongated, stretched into a bar, a long, roughly cigar-shaped concentration of stars running clean across the middle of the galaxy, with the spiral arms springing from its two ends, rather than from a round hub. The Milky Way, it turned out, is a barred spiral, one of that large family of galaxies whose arms uncoil not from a circular center but from the tips of a central bar. This had been genuinely hard to establish, precisely because of where we sit. From our position out in the disk, we view the bar nearly end-on, foreshortened, its true length hidden along our line of sight, so that for a long time it masqueraded as an ordinary bulge. It is a little like trying to judge the shape of a long table while crouched at one end with your cheek to the wood. The length collapses into perspective, and only careful, indirect clues can reveal that the thing is long and narrow rather than round. It took 2 lines of evidence to expose it. Infrared maps showing that one side of the central glow was subtly brighter and nearer than the other, exactly as a bar tilted toward us would appear, and the motions of stars and gas near the center, which traced out the elongated, streaming orbits a bar produces, rather than the simple circles a round bulge would allow. The bar is not idle either. Its gravity sweeps gas inward from the disk, funneling raw material down toward the very center, feeding the heart of the galaxy. Driven inward by the bar, that gas gathers into a dense ring near the middle and fuels bursts of new star formation there, a compact zone of activity wrapped around the core. The bar works, in effect, as a slow conveyor, ferrying the disk's raw material toward the center over hundreds of millions of years and reshaping the inner galaxy as it turns. And at that very center, at the still point the entire wheel turns around, sits something remarkable. In 1974, radio astronomers found a small, intense, and peculiarly compact source of radio waves at the exact dynamical center of the Milky Way, in Sagittarius, and named it Sagittarius A star. It was tiny, far smaller than any star cluster, and it sat precisely where the mathematics of the galaxy's rotation said the center of mass had to be, the pivot of the whole turning structure. For all that it marks the most extreme location in the galaxy, this central source is, by the standards of the wider universe, strikingly calm. Not a blazing beacon flooding space with radiation, as the violently active centers of some galaxies are, but a quiet, dim point, mostly dormant, betraying its presence chiefly through its gravity, rather than its light. The question was what it could possibly be, something compact enough to fit in a space smaller than our solar system, yet anchoring a galaxy of hundreds of billions of stars. The answer came from watching stars move. Over more than 2 decades, 2 teams of astronomers, one led by Reinhard Genzel in Germany, the other by Andrea Ghez in California, used the largest telescopes on Earth, working in the infrared to see through the dust, to track individual stars orbiting Sagittarius A star, photographing the very center of the galaxy year after year, and following the stars as they swung around the unseen point. It was painstaking, long-haul work. A star that far away creeps across the sky by the merest fraction of a degree, even over years, and only the steadiest instruments and the most patient tracking could trace a whole orbit at all. One star in particular, known as S2, traced out a tight, elongated orbit with a period of only about 16 years, swinging in close to the center and then racing out again, moving at its nearest approach, at thousands of kilometers every second. An orbit is a confession. From the size and speed of S2's path, the astronomers could weigh whatever it was circling, with great precision, and the answer was staggering. The thing at the center holds about 4 million times the mass of the Sun, packed into a volume smaller than the orbit of that single whipping star. Nothing known to physics can be that massive and that compact and remain dark and quiet except one kind of object, a supermassive black hole. The work earned Genzel and Ghez a share of the Nobel Prize in 2020, and in 2022, a global network of radio dishes managed to capture an actual image of the glowing matter encircling it, confirming directly what the orbiting stars had implied for years. But here is the part that matters most for the shape of the galaxy, and it is the opposite of what one might expect. For all the drama of a 4 million sun black hole at the center, it is, gravitationally, a minor character. 4 million suns sounds immense, and it is. But the Milky Way contains well over 100 billion stars, and the black hole's mass is a vanishingly small fraction of the whole, less than 1,000% of the galaxy's stars. This runs hard against intuition. The black hole is the most dramatic single object in the Milky Way, and it is natural to imagine it ruling the galaxy the way the Sun rules the solar system. But the Sun holds very nearly all the mass of its system, and the black hole holds almost none of its galaxies. Its fierce grip reaches only a short way out, dominating the orbits of stars in its immediate vicinity, like S2, and then fading into irrelevance. Out where we are, 26,000 light-years away, the central black hole pulls on us no more strongly than an ordinary star of its mass would at that distance, which is to say hardly at all. It is the anchor that marks the center, the pivot of the wheel, but it is emphatically not the thing that holds the wheel together. The Sun does not orbit the galaxy because of the black hole. Almost none of the galaxy does, which leaves a glaring question hanging over everything mapped so far. If the central black hole is too slight to govern the disk, and the visible stars and gas, added all together, do not come close to enough either, then what is holding this enormous rotating structure together? What keeps the outer stars from simply flinging themselves off into the dark? By every honest accounting of the visible matter, every star, every cloud of gas, every grain of dust, with the central black hole thrown in for good measure, there was simply not enough mass in the Milky Way to hold itself together at the speed it was turning. The answer had, in fact, been sitting in plain sight all along, hidden inside the very rotation the radio astronomers had measured so carefully, in a single number that, when anyone stopped to check it, refused point-blank to behave. The number that would not behave was the rotation speed of the galaxy, plotted against distance from the center. Draw a graph with distance from the galactic center running along the bottom and orbital speed up the side. Mark on it how fast the stars and gas are moving at each distance, and you have what astronomers call the rotation curve. It is one of the most important graphs in the history of the subject, and what it shows should have been impossible. To see why, look first at the solar system, where the same kind of graph behaves exactly as it ought to. Nearly all the mass of the solar system is gathered into the Sun at the center. Mercury, close in, races around at huge speed. Earth, further out, moves more sedately. Neptune, far away, crawls. Mercury rounds the Sun in a matter of months. Distant Neptune needs 160 years to complete a single orbit. The orbital speed falls off steadily with distance, because the further a planet sits from the central mass, the weaker the gravity holding it, and the slower it needs to travel to keep its orbit. This is a firm, well-understood law. If the Milky Way's mass were likewise concentrated where its light is, piled up in the bright bulge and the inner disk, thinning out where the stars thin out, then its rotation curve should do the same thing. Stars and gas far from the center, out where there is little visible matter left, ought to orbit slower and slower the further out they lie, the curve sloping gently down toward zero. It does no such thing. When the rotation of the Milky Way was traced outward, and the 21-centimeter hydrogen surveys were perfect for this, because hydrogen gas extends far beyond the visible stars, and its Doppler shifts give it speed directly, the curve did not fall. It rose, leveled off, and then simply stayed flat, stretching out at the same high speed, around 230 kilometers a second, far beyond the edge of the luminous disk, out into regions where there is almost no visible matter at all to be seen. The hydrogen could be tracked far past the last bright stars, out where the disk fades away to nothing, and still it came round at full speed, lap after lap, as though the galaxy's edge were not really its edge at all. The outer gas was orbiting just as fast as material much closer in. By every rule that governs the solar system, that gas should long ago have flung itself off into intergalactic space, because there was not nearly enough visible mass out there to hold something moving so quickly, and yet it stayed, bound, circling obediently, as though held by a great weight that simply was not showing up in any telescope. There was only one way to read it. The mass of the Milky Way does not stop where the light stops. Something massive and invisible must extend far beyond the glowing disk, a great reservoir of unseen matter whose gravity reaches out and grips the fast-moving gas in the outskirts, holding it on its orbit. The flat rotation curve was, in effect, a weighing of the galaxy by its own motion, and the scales kept reading far heavier than everything that shone. The faster-than-expected outskirts were not breaking the law of gravity. They were obeying it, around a quantity of matter no one could see. And it was not some small discrepancy to be argued away at the edges. To hold the outskirts at the speeds observed required several times more mass than every visible star and cloud combined could supply. The shortfall was not at the margins of the accounting. It was most of the accounting. The astronomer who pinned this down, more than anyone, was Vera Rubin, working in the 1970s with the instrument builder Kent Ford. There had been earlier hints. Back in 1932, Jan Oort, the same Oort who would later drive the Dutch radio program, had noticed that the stars near the sun seemed to be held to the disk by more gravity than the visible stars could supply, an early whisper of missing mass. Others had seen excess weight in great clusters of galaxies. But Rubin and Ford made it undeniable. Using a sensitive spectrograph that Ford had built, they measured how fast the gas was orbiting at point after point across the face of the neighboring Andromeda galaxy, and then across dozens of other spirals. Building rotation curve after rotation curve, every one of them came out flat. Galaxy after galaxy was spinning too fast in its outer reaches to be held together by its visible stars alone, and all of them, our own included, had to be embedded in something heavy and dark. Rubin's measurements were careful, patient, and difficult to argue with, and they did more than any theory to force the astronomical world to accept that most of the matter in a galaxy is invisible. She had come up in a field that often made little room for her, at times shut out of the very observatories whose telescopes she needed, and she had chosen rotation curves partly because they were quiet, unfashionable work where she could labor without rivalry. That unglamorous choice turned out to uncover one of the largest facts about the universe. Like Leavitt before her, she did the foundational observational work and watched much of the glory settle elsewhere. She never received the Nobel Prize many felt she had earned. What the rotation curves revealed is now part of the basic picture of our galaxy, and it is humbling. The Milky Way is wrapped in a vast, roughly spherical halo of dark matter that extends far beyond the visible disk in every direction, dwarfing the bright galaxy in both size and mass. It reaches outward perhaps several times the radius of the luminous disk, a great dark sphere with the shining galaxy suspended at its very heart. The stars and gas we can see, the whole glowing pinwheel that Herschel and Shapley and Oort spent lifetimes mapping, are only the luminous core of something far larger and entirely dark. By weight, this unseen halo outweighs all the stars and all the gas of the Milky Way together by something like 5 or 6 to 1. The galaxy we can photograph is the small, bright minnow swimming inside a great invisible whale. And it is this halo, not the central black hole and not the visible disk, that supplies most of the gravity holding the whole structure together and governing how it turns. The thing that answers the question left hanging at the center, what keeps the outer stars from flying away, is a form of matter that gives off no light, no radio, no signal of any kind, and announces itself only through its pull. What this dark matter actually is remains one of the deepest unanswered questions in all of science. Its identity is genuinely unknown, and untangling it is a vast investigation in its own right, well beyond the shape of one galaxy. But for the purpose of understanding the Milky Way, its role is no longer in doubt. It is the hidden scaffolding the visible galaxy is built upon, the dark framework inside which the disk can spin without tearing itself apart. The true shape of the Milky Way, properly drawn, is mostly a shape we cannot see. There is a strange humility in that. Looking back over the whole long effort, generation after generation strained to chart the band of light overhead, counting its stars, timing its pulses, listening to its hydrogen, piercing its dust, and built, in the end, a magnificent map of what turns out to be the small, shining exception. The galaxy is mostly the dark we never plotted, and the luminous spiral we worked so hard to draw rides quietly at its center, like a single candle lit in the middle of a darkened room. With the halo finally added in, the inventory of the galaxy is at last complete. A dark and dominant halo, a disk of stars and gas, the great spiral arms turning through it, a barred bulge of ancient stars, and a quiet black hole pinning the center. But an inventory is not a history. Knowing what the parts are does not tell us how this particular structure came together, nor how it manages to hold its graceful form steady, while everything within it streams and turns and is slowly rearranged. For that, we need to meet the force that has been doing the shaping all along. The force that shaped all of it is gravity, the same gentle, relentless pull that holds you in your chair. Every structure we have mapped, the flat disk, the winding arms, the central bar, the swarming halo of clusters, the dark halo enclosing everything, is gravity's handiwork, accumulated over billions of years. Gravity gathers. It draws matter toward matter, patiently, without pause, building concentration out of emptiness. Left entirely to itself, though, gravity has only one ending in mind: total collapse, everything falling together into a single point. A galaxy held by gravity alone, and nothing else, would crush itself out of existence. Something has to hold it open. That something is rotation. The Milky Way survives as an open, graceful structure because gravity's inward pull is balanced, almost everywhere, by the orbital motion of the matter within it. Stars and gas do not fall into the center because they are moving sideways, fast, circling rather than plunging, and that sideways motion, that spin, keeps them aloft in exactly the way a stone whirled on a string stays out from your hand rather than dropping to your feet. Gravity pulls in, orbital motion carries past. The two settle into a standoff, and the standoff is the galaxy. Tip the balance either way, and the structure cannot survive. Slow the rotation, and gravity wins, dragging everything inward toward collapse. Speed it up, or weaken the gravity, and the orbits open out until the galaxy unbinds and scatters into the dark. The Milky Way exists in the narrow margin between those two fates, a vast structure poised for billions of years, on a balance it never has to think about. This balance even explains the galaxy's basic geometry, the puzzle of why it has the shape it does. A cloud of gas with any overall spin, as it collapses under its own gravity, cannot fall straight inward, because its rotation resists collapse in the plane of the spin, while doing nothing to resist it along the axis. So it flattens, settling into a thin, spinning disk. The same reason the solar system is flat. The same reason a ball of pizza dough spreads into a disk when it is spun. The Milky Way's disk is thin and flat, precisely because it rotates. And the halo, which has very little overall spin, has no such constraint, which is exactly why it stays puffed up into a great rough sphere rather than flattening. Shape, in the end, is the fingerprint of motion. The disk is flat because it turns. The halo is round because it does not. But the galaxy we see was not poured into this shape ready-made. It has a history, and that history is violent. Big galaxies grow by eating smaller ones. The Milky Way assembled itself over billions of years, not in one smooth piece, but by drawing in, tearing apart, and swallowing a long succession of smaller galaxies that strayed too close, folding their stars into its own. Our galaxy is, in the most literal sense, a survivor and a cannibal, built from the remains of the companions it has consumed. The largest of those ancient meals has a name, and we can still see its leftovers. Around 10 billion years ago, when the Milky Way was young, it collided with and absorbed a substantial dwarf galaxy, an event astronomers call Gaia Enceladus, or sometimes simply the sausage, after the curious shape its stars trace when their motions are plotted. That swallowed galaxy was large enough to leave a permanent mark. A great many of the stars now wheeling through the inner halo of the Milky Way are not native to it at all. They are the scattered, digested remains of Gaia Enceladus, still moving on the long, plunging orbits they brought with them from another galaxy entirely, 10 billion years after their home was destroyed. We did not even know they were intruders until very recently, when a survey precise enough to measure their individual motions revealed that a whole population of nearby stars was marching to a different drummer, the fossil signature of an ancient collision written into the orbits of stars we can see in the sky tonight. It was a major event in the building of our galaxy, not some minor snack. That single swallowed dwarf may have supplied a large share of the entire inner halo, and the violence of its arrival helped stir up and thicken the older layer of the disk as it crashed home. That meal was not the last, and the evidence of others is strewn all around us. At this very moment, the Milky Way is in the act of devouring a smaller companion, the Sagittarius dwarf galaxy, which is being stretched and pulled apart as it falls through our disk. Its stars drawn out into an enormous stream that loops right over the galaxy like a ribbon caught on a wheel. The halo is laced with such streams, long, thin trails of stars, the shredded remains of dwarf galaxies, and star clusters torn apart and stretched into filaments by the Milky Way's tides, each one the fading wake of something the galaxy ate. The Dutch-based astronomer Amina Helmy, working at Groningen, the same Groningen where Kaptein had built his flawed lens a century before, was among the first to find these streams and to read them as the relics of past mergers. Reading them is a kind of archaeology written in starlight, because a stream of stars keeps, for billions of years, the memory of the orbit on which its parent galaxy fell in. Astronomers can run the motions backward and reconstruct meals that finished long before the Earth existed. And out beyond the disk hang the Magellanic Clouds, those same two smudges where Leavitt found her pulsing stars, companion galaxies now slowly falling toward us, trailing a long stream of gas torn from them by our gravity, future meals in their own slow approach. All of this churning leaves the galaxy marked. The outer disk of the Milky Way is not flat but warped, bent upward on one side and downward on the other, like the brim of a hat or a vinyl record left too long in the sun. This warp is almost certainly the work of the same gravitational disturbances, the tugging of the Magellanic Clouds, the wakes of past encounters, the sloshing left by ancient meals that have shaped the galaxy throughout its life. Recent measurements have even shown that the warp is slowly shifting its orientation over time, wobbling as the galaxy turns. The same surveys have found faint ripples and ridges running through the disk as well, the settling vibrations of recent encounters, as though the galaxy were a great pond still trembling from stones thrown into it long ago. The Milky Way is not a finished, static object sitting quietly in space. It is dynamically alive, still being pushed and pulled, still rearranging its edges, still digesting its past. And yet, through all of it, the essential form endures. This is the deep lesson of the galaxy's history. Stability is not the absence of change, but the ability to absorb it. The dark halo cushions the blows of incoming galaxies, spreading their impact gently across the whole structure. Mergers that might tear a fragile system apart are instead folded in, their stars woven into new orbits, their gas added to the reservoir, while the thin disk, remarkably, stays thin and orderly across billions of years and dozens of rotations. The Milky Way has been struck, stretched, and fed upon throughout its existence, and it has answered every disturbance not by breaking, but by incorporating. It even has its next great event already in view. In some 4 or 5 billion years, the approaching Andromeda galaxy will meet our own, and the two great spirals will merge into something new. It will be, seen from far enough away, a slow and almost graceful event. The two disks, swinging together over hundreds of millions of years, their stars so widely spaced that scarcely any will ever actually collide, the whole encounter resolving in time into a single, larger galaxy. The galaxy endures, in other words, precisely because it bends. We have now rebuilt the whole thing from the inside, its parts, its motion, its hidden mass, and its long and violent past, without ever once stepping outside it, which raises an obvious and unnerving question. After all this careful inference, all this reasoning in the dark, how could anyone ever know whether the picture is actually right? There is, as it happens, one way to check. We can look outward, at other galaxies, seen whole and entire from the outside, and ask whether the thing we so painstakingly deduced about our own looks anything like the real spirals hanging in the depths of space. We will never photograph the Milky Way from outside. No camera will ever be carried far enough above the disk to capture our galaxy whole, the way we so easily capture others. But that limitation hides an unexpected gift. The universe is full of other galaxies, hundreds of billions of them, and a great many are spirals, hanging at every angle in the depths of space, some turned conveniently face on, so that their entire structure lies open to view at a glance. We cannot step outside our own galaxy, but we can step outside theirs. And so the test of our long, painstaking, inside-out reconstruction was simply this. Go and look at the spiral galaxies we can see whole, and ask whether any of them match the blueprint we had deduced for our own. It is a curious reversal. The one galaxy we can never see from outside is the very one we live in. Every other galaxy in the universe, we can only ever see from outside. We are blind to ourselves and clear-sighted about everyone else, and the whole trick was to use the second fact to repair the first. They do, and the match is exact in every important respect. Out among the galaxies are barred spirals that could serve as portraits of the Milky Way, a straight bar of stars across the center, spiral arms uncoiling not from a round hub, but from the two ends of that bar. A flattened disk, a bulge of old stars at the core, and along the inner edge of each bright arm a sharp, dark lane of dust, with the arms themselves picked out in the blue glow of newborn stars against the smoother golden light of the older disk. Every feature we had inferred for our galaxy from the inside, the bar we saw end on, the density wave arms, the dust we proved by its reddening, the blue nurseries, the old central bulge, was there to be seen plainly in galaxies like NGC 6744 and NGC 1300, written across the sky for anyone to read. Even the subtler details lined up. The arms of these galaxies are patchy and uneven, some grand and sweeping, others breaking into spurs and fragments. exactly the messiness the Milky Way's own arm structure shows. The disks are thin, the bars turn slowly, the dust threads through in the same dark filaments. Nothing about our reconstruction stood out as wrong when it was held up against the real thing. Astronomers point to certain of these barred spirals as near twins of our own, and the familiar face-on portrait of the Milky Way that appears in every book is, in truth, a composite. Our own internal measurements of distances and motions fitted onto the visible template of the galaxies out there that most resemble us. When you see that golden pinwheel with its glowing bar and its neatly labeled arms, you are not looking at a photograph of the Milky Way. You are looking at a careful inference, a portrait pieced together from measurements taken inside the disk and dressed in the likeness of our nearest lookalikes. There is something quietly profound in that. We came to know our own face by studying the faces of strangers. Unable ever to see ourselves directly, we recognized ourselves in others, confirmed the shape of the structure we live inside by finding it, again and again, hanging in the dark 100 million light years away. The inside-out map and the outside-in portrait agreed, and that agreement is as strong a confirmation as this kind of science can offer. Consider how strange the situation is. A person can never truly see their own face directly. They know it only from mirrors and photographs, from reflections, and from the recognition of others. The Milky Way is in exactly that position, and astronomers found its mirror not in glass but in the depths of space, in the reflected likeness of distant galaxies that happen to be built the same way we are. Set against that great population of galaxies, the Milky Way turns out to be strikingly ordinary, and ordinary in a particular and meaningful way. It is a middling to large barred spiral, neither a giant nor a dwarf. Its rate of making new stars is moderate, not the furious blaze of a starburst galaxy converting its gas in a brief, brilliant frenzy, nor the silence of an old galaxy that has used up its fuel and gone quiet and red. It forms a few new stars a year, steadily, and has done so for a very long time. Some galaxies are caught forging hundreds or even thousands of stars a year, blazing through their gas in a cosmic eye blink. Others, vast and old, have not made a new star in ages and glow only with the dimming red light of their ancient ones. The Milky Way sits quietly between these extremes, a slow and frugal furnace, neither flaring nor failing. Its history, as we have seen, has been comparatively gentle. It has eaten smaller galaxies, but it has avoided the kind of head-on collision with an equal that would have wrecked its disk and scrambled it into a shapeless ball. Its disk has stayed thin and well-ordered. In almost every measure one might choose, the Milky Way sits comfortably in the broad middle of the range, unremarkable, unexceptional, average. If an observer in some other galaxy were cataloging the spirals of the universe, ours would barely earn a second glance. And that, far from being a disappointment, may be the most important thing about it. The galaxy's very ordinariness is bound up with its endurance, and its endurance is bound up with our being here. Galaxies that burn brightly burn briefly, spending their gas in a single spectacular generation of stars, and then falling dark. Galaxies torn apart by violent mergers have their orderly disks destroyed, their stars flung into chaotic orbits, their quiet rhythms broken. The Milky Way did neither. It chose, through nothing but physics, the slow and moderate path, forming stars at a measured pace, absorbing its companions gently, keeping its thin disk intact across more than 10 billion years. That long, unspectacular steadiness is precisely the condition under which planetary systems can settle into stable orbits and remain there, undisturbed, for the billions of years that complex life appears to require. Every spectacular alternative is, in this sense, hostile to long, slow projects. A starburst exhausts itself before much can develop. A wreck scatters whatever order had begun to gather. Only the patient, middling galaxy offers the one thing biology, as far as we know it, cannot do without: time, in great unbroken quantities, beneath a steady sky. The Milky Way's lack of drama is not a flaw in its character. It is the reason there has been time enough and calm enough for anyone to evolve within it and look up and begin to work out its shape. We are, in a real sense, children of its moderation. It would be wrong to overstate this and call the Milky Way perfectly average in every detail. It has its own peculiarities, an unusually large pair of companion galaxies in the Magellanic Clouds among them, and in some respects, it is a little quieter even than its size would predict. But the broad verdict holds. Our galaxy is a typical example of a common kind, shaped by the same universal laws that shape its countless siblings. Special to us not because it stands apart, but because it is ours, and because its particular, ordinary steadiness is what made us possible. The outside view confirmed the inside one, and the picture could have rested there, complete in its broad strokes. But the inside view itself was about to become almost unimaginably sharper. For most of this story, the map of the Milky Way had been drawn in broad arcs and soft edges, assembled from gas surveys and statistics and careful inference. Then a single spacecraft, hanging quietly in space, set about measuring the precise positions, distances, and motions of more than 1 billion individual stars, and turned the old hand-drawn chart of our galaxy into something alive, three-dimensional, and breathtakingly exact. The spacecraft was Gaia, launched by the European Space Agency in 2013 and stationed at a gravitationally calm spot about 1.5 million kilometers beyond the Earth, on the far side from the Sun, where it could turn slowly and stare at the sky without interruption. Spinning steadily and sweeping its gaze across the entire sky, again and again, it returned to each star not once but scores of times over the years, each visit refining the measurement a little further. Its single purpose was to measure stars, not their chemistry or their physics, but simply, and with fanatical precision, where they are and how they move. Over more than a decade of patient scanning it, fixed the positions, distances, and motions of nearly 2 billion stars, around 1 in every 100 stars in the entire galaxy, building a census of the Milky Way, of a kind that Herschel, counting by eye at his telescope, could not have imagined in his wildest hopes. 2 billion is a number that resists imagination. If you set out to count Gaia's stars 1 per second, without ever stopping to sleep, you would not finish in the whole span of human history. And for each of those stars, the spacecraft recorded not a single fact, but a small dossier, a position, a distance, a direction, and a speed, so that the catalog is less a list than a moving, three-dimensional model of a large piece of the galaxy. The heart of what Gaia did was to measure distance directly, by the one method that assumes nothing at all: parallax. As the spacecraft circles the Sun along with the Earth, a nearby star appears to shift its position very slightly against the far more distant background, first one way and then the other. Over the course of a year, the same effect you see when you hold a finger up and look at it with one eye, then the other, and watch it jump against the wall behind. The nearer the star, the bigger the jump. Measure the size of that tiny shift, and simple geometry gives you the distance, with no guesswork about how bright the star ought to be. This is the firmest distance measurement there is, the very bottom rung of the whole ladder that Leavitt's pulsing stars were built on top of. And it had always been agonizingly hard, because the shifts are so minute. Gaia measured them for over 1 billion stars, to a precision almost impossible to credit, angles equivalent to the width of a human hair seen from 1,000 kilometers away. For the first time, the depth that had defeated everyone since Galileo was being read off directly, geometrically, star by star by star, across a vast swathe of the galaxy. And in nailing down those geometric distances, Gaia did more than chart our neighborhood. It re-anchored the entire distance ladder, every rung above it, Leavitt's Cepheids included, now resting more firmly than ever on a foundation of stars whose distances had been measured outright, with no assumption at all. And because Gaia measured not just where the stars are, but how they move, it did something no earlier survey could. It turned the map into a movie. With precise positions and precise motions for 1 billion stars, astronomers could run the galaxy's clock forward to see where everything is heading, or backward to see where it has been. The Milky Way stopped being a still photograph and became a living, moving system that could be played in either direction. And when they did play it, the disk came alive in ways no one had expected. The warp at the galaxy's edge was caught slowly turning. The buried wreckage of the Gaia-Enceladus collision was pulled out of the tangle of stellar motions, an entire devoured galaxy reconstructed from the orbits of its scattered dead. And running through the disk was a delicate, unexpected spiral pattern in the motions of the stars themselves, the sign of a disk still ringing, still vibrating from some disturbance in the recent past, like the fading shiver of a bell that was struck a few 100 million years ago and has not quite gone still. Most likely the bell was struck by the Sagittarius dwarf, the small galaxy still falling through our disk, its passage setting the whole vast plate of stars quietly trembling. We are, it turns out, living inside the slowly fading aftershock of a collision, a disk that is not perfectly settled but still faintly humming from its own recent history. There is a clean line running from the very beginning of this story to that spacecraft. Herschel had stood at his telescope and counted stars, direction by direction, trying to find the shape of the galaxy by tallying its lights, defeated in the end because he could not measure their distances and did not know about the dust. Gaia is Herschel's dream made real. The same counting of stars, the same attempt to find the shape of the Milky Way from the inside, but now with the true distance to each one measured directly, the dust mapped and accounted for, and not hundreds of stars, but nearly 2,000 million. The question never changed across 2.5 centuries. Only the precision did, growing from a careful guess into a measurement of breathtaking exactness. Every figure who has appeared in this story is a link in that one long chain. Leavitt cutting the first true rung of the ladder, Shapley using it to move us off the center, Trumpler exposing the dust, Van de Hulst and Oort learning to listen through it, Rubin weighing the dark that no one could see, each of them extending the work rather than overturning it, each handing the problem on a little more solved than they had found it. And yet, and this matters as much as any triumph, the map is still not finished, and from where we sit, it never can be. The dust that defeated the first map makers has not gone away. Gaia sees by starlight, and starlight still cannot cross the thickest reaches of the disk, so the far side of the galaxy, the half that lies beyond the crowded center, remains dim and poorly charted, sketched in far less certainty than our own bright neighborhood. It is a strange thing to admit of a galaxy we have mapped so well, but there is an entire far hemisphere of the Milky Way that no one has ever clearly seen. Arms and clouds and clusters on the other side of the center, hidden behind the glare and the dust, known today only in rough outline. The exact number of the spiral arms is still genuinely argued over. Whether the Milky Way has 2 grand arms or 4, how many of the features are major arms, and how many mere spurs, where precisely each one runs. The full length and behavior of the central bar are still being pinned down, and the dark halo that outweighs everything remains the deepest unknown of all, its very substance unidentified, even its exact shape, whether it is a smooth sphere or something flattened or lumpy, still uncertain. These are not embarrassments. They are the live edge of the map, the places where the work is still going on, and they are exactly what one should expect from a structure so vast being charted by observers who can never leave it. To map a galaxy from the inside is to accept that the picture will always be sharpest close to home and softest at the far horizon. So we are left with a portrait of the Milky Way more precise and more alive than any generation before us has held, and still, honestly, incomplete, a structure known well enough to be understood, not so well as to be closed. Which brings the whole long journey back to the simplest question of all, the one that has been waiting quietly underneath every measurement from Herschel's star gauges to Gaia's billion parallaxes. We have worked out, against tremendous odds, what shape we live inside. The question that remains is why that shape should matter at all, what it actually does, and why getting it right tells us something about ourselves. The shape matters because shape is not decoration. The arrangement of a galaxy is not a picture laid over it. It is the thing that decides how the galaxy behaves. Every structure we have traced does work. The flat disk, the central bar, the spiral arms, the dark halo enclosing them all. Each one governs how matter within the galaxy moves, where it gathers, what becomes of it. Change the shape, and you change everything that happens inside it. The form is the cause, not the consequence. We tend to think of a thing's shape as the least of its properties, a surface detail, the outline left over once the important business is done. For a galaxy, it is the other way round. The shape is the important business. It is the slow outcome of gravity and motion and time negotiating with one another across billions of years, and once it is settled, it turns around and sets the terms of everything that happens next. Consider what the shape actually does. It is the structure that decides how stars move, setting every orbit in the galaxy, the disk holding stars on their long circular paths, the bulge and bar steering the crowded inner orbits, the dark halo gripping the outer reaches and keeping the whole thing from flying apart. Without that structure, stars would not trace stable, predictable routes. They would wander and scatter, and there would be no orderly galaxy at all. The neat, repeating motions that make the night sky look so permanent are not a given. They are a gift of the structure, the disk keeping its members in step like dancers who turn together and never collide. The shape also decides where stars are born. The spiral arms gather the cold gas and squeeze it, pacing the birth of new stars across the disk, controlling the rhythm so that the galaxy makes its stars steadily over billions of years, rather than burning through them in one wild and barren flash. And in those same squeezed clouds, the very grains of dust we met long ago, the stuff that hid the galaxy for so long, gather into pebbles and worlds, so that the shape of the Milky Way sets not only where its stars are lit, but where its planets are laid down beside them. And the shape decides whether the galaxy lasts. The fine balance of gravity against rotation, the cushioning bulk of the halo, the moderate and unspectacular career, these are what allowed the Milky Way to hold its form for more than 10 billion years, to absorb its collisions and keep its thin disk intact, to endure. A more dramatic galaxy would have spent itself long ago, or torn its own disk to pieces in some great collision, and there would have been no steady sky beneath which anything slow could unfold. And here the whole long story folds back on itself, because that endurance is the reason any of it could be told. A galaxy that holds steady for billions of years, that keeps quiet, calm regions far from its violent center, that paces its star formation gently and settles its planets into stable orbits, that is a galaxy in which there is time. Time for a cloud of gas and dust, kindled in some spiral arm, to collapse into a star and its worlds. Time for one of those worlds, drifting in a peaceful spur far out in the disk, to cool and gather oceans and grow the slow chemistry of life. Time for that life to climb, across hundreds of millions of years and a good fraction of a galactic orbit, from the simplest beginnings to creatures who could stand on the surface of that world and look up. We are not visitors to the Milky Way. We are made of it, our atoms forged inside its earlier stars, scattered by their deaths, gathered in its arms, carried on its slow rotation to the quiet place where we happen to sit. Every iron atom in your blood, every grain of calcium in your bones, was cooked inside a star that lived and died in this galaxy before the sun was ever born, then drifted as dust and gas through the arms until it was swept into the cloud that became the sun, the earth, and you. The Milky Way is not the backdrop to our existence. It is the source and the substance of it, and its long, patient shape is the only reason the chain held together long enough to reach us. The shape of the galaxy is written into the fact of our existence. We are one of the things its shape produced, which leaves the strangest product of all. Of everything the Milky Way's shape has made across more than 10 billion years, the stars and the arms, the clusters and the streams, the worlds beyond counting, the strangest is surely this, a structure that, on at least one small world, gave rise to observers who could turn around and work out the shape of the structure itself. People sealed permanently inside the galaxy, unable ever to step outside it, reasoned out its true form anyway, from the rhythm of a pulsing star, measured by a woman at a desk in Massachusetts, from the swarm of clusters that pushed us off the center, from the dust proven by clusters too faint for their size, from a faint note of hydrogen predicted in an occupied country and traced into spiral arms by patient dishes on the heathland, from a flat curve that revealed the dark, from a spacecraft counting 2 billion stars. Each of them passed the problem on a little more solved. Between them, the inhabitants of one quiet spur drew the map of the whole vast wheel they were riding. None of them saw the finished picture. Each added a single rung, a single measurement, a single stubborn fact, and handed it on. A woman timing the pulse of a distant star never knew her work would one day weigh the galaxy. A young man reasoning in a blacked-out city never lived to hear, with his own ears, the signal he had predicted traced into spiral arms. They simply did the next piece of the work and trusted the rest to those who came after. In a real and literal sense, the Milky Way, through them, has slowly come to know its own shape. The galaxy looked at itself and, after a very long time, began to understand what it was looking at. It is worth holding that thought, because nothing in the laws of physics required it. A galaxy can turn for 10 billion years and never once contain a single thing that knows it is turning. Ours, somehow, came to. The same gravity that sculpted the disk also, by the longest and most roundabout of routes, assembled minds capable of sketching that disk on paper. The map and the mapmaker are both the galaxy's own handiwork. If you enjoyed this journey into the hidden shape of our galaxy, a like or a subscribe helps us continue making them. So the next time you stand beneath a truly dark sky and catch that faint band of light arching overhead, look at it again and see it for what it is. It is not a smear on the night, nor weather, nor a stain of spilled milk. It is the edge-on view, from one small room inside it, of the only home our kind has ever had, a barred spiral 100,000 light-years across, turning slowly through the dark, carrying its dust in its arms, Its ancient bulge and its hidden weight and its single world of watchful observers, around a center none of them will ever see with their own eyes. We could never step outside it, so we did something stranger instead. We drew the room from the inside by the light of its own stars, and we hung the finished map upon its walls. The universe still has plenty left to reveal, and we will be following it as it does.